Okay, so just to go into the answer here, we have a dad model and a not dad model. Just to make the hopefully fairly straightforward point, when we talked about the not dad model basically being that the child and putative father are actually not related, they're just random unrelated people from the population, then that pretty much looks exactly the same as what we had been using as our mismatch model in the forensics test case. In other words, the only thing that connects these two sample measurements, S and C, then is simply the population allele frequency of this SNP marker in the population theta. Turning now our attention to the dad model, now the assertion is that in this way that we did for our very first genetics information graph problem, that basically the genetic state of the child depends upon the genetic state of the father, right? So remember that we said we weren't including mom at all in this measurement experiment. So we've left mom out of the information graph. I'll talk more about that in a moment, about the whole issue of is it useful or not to include mom, but for the moment, you know, we can keep things simple and say we're not including a hidden variable for mom. So what we've proposed here is basically a hidden variable kappa, genetic state for dad, and lambda, a genetic state hidden variable for the child, and we've simply got an edge going from kappa to lambda, and we've also, in the absence of a hidden state variable for mom, we're basically just drawing an edge straight from theta through to lambda. In other words, p lambda is basically conditioned upon two hidden variables, namely kappa and theta. Okay? Question?
So we're not treating like the father and the son like they were the same, but we're saying that kappa affects lambda, so the father affected the...
Right, exactly. And this kind of gets back to this idea of modeling causality, that we propose basically a hidden process that we believe emitted our observables, right? And then we can use Bayesian inference to go backwards to reverse that and make inferences about hidden variables. Question?
Did we need to include a line from theta to lambda?
Okay, so that's a really good question. Do we need to include a dependency of theta going to lambda? So this really is kind of the implicit representation of mom in this information graph. If you put mom in, which you could do, we wouldn't call that wrong, there'd be a hidden variable in between lambda and theta, which would represent a genetic state for mom. But I think what you could see is having mom in there would simply be a way of connecting lambda to theta besides just going through kappa. So if you think about it, you know, that's the real process, that child's genetic state depends upon mom and dad. If we're not including mom explicitly, then that edge that's going from theta through mom to child, it still has to be captured. In other words, one way of saying that is the child's genetic state does not depend solely on dad, right? I mean, for example, the question of whether this is a really common polymorphism or a really rare polymorphism, that still matters for assessing the probability of lambda, even if we know kappa, right? So for example, if kappa was 0, and now we're trying to make inferences about the value of lambda, it would make a big difference if theta was a really big value, right, as opposed to a really tiny value. So that's why there's an edge there. That was a great question. Question?
So if we
Right, exactly. So it would look very much like the way kappa is contributing here, except that we don't have a observable sample measurement from coming off of mom. So basically there'd just be another hidden variable sitting right there. Great question. Other questions?
So, no sample from mom is included in this analysis. Does that mean the lambda equals to 0 and 1? Is there...
Okay, so you're raising an interesting point. So I didn't say there was no mother. I simply said we don't have any observable data telling us about the mother's genetic state. That was sort of the assumption for this exercise. That just, you know, we're not considering mom. We don't have experimental data, one of these observable measurements for mom. But, you know, the possible values for lambda are still 0, 1, or 2. We're, you know, treated as a regular genetics kind of problem. Other questions? Okay. So if you do the self-assessment, you'll be offered some possible common errors that people sometimes make in how they're thinking about this, and I think you can pretty much follow up on that outside of class, unless people specifically want me to go through this right now. Okay, well, if you made any of these mistakes, you know, take a look outside of class. Okay, so one point that I want to get at here is this issue of the individual copy number variables representing hidden genetic states. So things like kappa, how they matter here. Just to go back to our model, you know, one very clear reason why we had to have kappa and lambda in this picture is because they are what connect the observations S and C in our DAD model, right? So connectivity of our observables is a key criterion for thinking about what is truly required. You can't get rid of it because it represents actually how the data are going to behave, how they're connected to each other. Okay? Any questions about this connectivity issue and how it drives your choices about modeling?